Hello there, and welcome to Whispered Knowledge. I'm so glad you found your way here tonight. Maybe you've had a long day, or perhaps you're simply drawn to the kind of deep, cosmic wonder that helps the mind settle and the body relax. Either way, you're in the right place. Tonight, we're going on a journey through 100 remarkable facts about our home planet, Earth. The blue marble spinning through space that has been our cradle, our provider, and our only known home for all of human existence. You don't need to do anything but rest. Let your breathing slow, your muscles soften, and your thoughts drift as we explore this extraordinary world together. From the planet's fiery birth over 4.5 billion years ago to the invisible magnetic shield protecting us right now, from the deepest ocean trenches to the highest peaks, we'll wander through the story of Earth with curiosity and wonder. Some of what you hear might surprise you. Other facts might feel familiar, like old friends returning to visit. All of it is meant to carry you gently towards sleep while reminding you of the remarkable planet we call home. And before we begin, if these calm explorations help you unwind at the end of your day, I'd be grateful if you'd consider liking this video and subscribing to Whispered Knowledge. It helps others find their way here too, one curious soul at a time. Now, let's begin our journey through 100 facts about Earth. The birth of a planet. Earth formed approximately 4.54 billion years ago. When we try to imagine such vast stretches of time, our minds struggle to grasp the magnitude. To put it in perspective, if Earth's entire history were compressed into a single 24-hour day, humans would appear only in the final second before midnight. The planet emerged from a vast cloud of dust and gas called the solar nebula, leftover material from the formation of our sun. Gravity pulled these particles together, and they began to stick, forming larger and larger clumps. Over millions of years, these clumps grew into planetesimals, then into protoplanets, and eventually into the world we know today. The early Earth was nothing like the serene blue planet we see from space now. It was a hellish realm of molten rock, extreme volcanism, and constant bombardment by asteroids and comets. The surface temperature exceeded 1,000 degrees Celsius. Rivers of lava flowed across the landscape. The sky glowed red with heat and volcanic ash. This period, known as the Hadean Eon, lasted from Earth's formation until about 4 billion years ago. The name comes from Hades, the Greek underworld, and it's fitting. No life could have survived in such conditions. The planet was still forming, still settling, still becoming what it would be. 3 mechanisms generated this incredible heat. First, gravitational compression as material fell inward created friction and warmth. Second, radioactive decay of unstable isotopes within the growing planet released energy. Third, and perhaps most dramatically, the constant impacts from space objects, some as large as small planets themselves, delivered enormous amounts of kinetic energy that converted to heat upon collision. Much of this primordial heat still exists deep within Earth's interior today, driving the convection currents that power plate tectonics and generate our protective magnetic field. During these early days, Earth experienced what scientists call the giant impact hypothesis. a Mars-sized body, which we've named Theia, collided with the young Earth in a catastrophic impact. The collision was so violent that it vaporized portions of both objects, sending debris into orbit around Earth. Over time, this debris coalesced and formed our Moon. Evidence for this theory comes from several sources. Moon rocks brought back by Apollo missions have a similar composition to Earth's mantle. The Moon has a relatively small iron core compared to other rocky bodies its size, and computer simulations of this type of impact produce results that match what we observe today. The Moon's formation had profound effects on Earth. It stabilized Earth's axial tilt, preventing wild variations in climate that would have made life difficult or impossible to establish. The Moon created tides in Earth's oceans, which may have played a role in the development of life, and the Moon gradually slowed Earth's rotation through tidal friction. Based on models of tidal evolution, scientists estimate that early in Earth's history, a day may have lasted only about 6 hours. Over billions of years, the Moon's gravitational pull has stretched each day longer, though we're talking about changes measured in milliseconds per century. As Earth cooled, the heaviest elements, primarily iron and nickel, sank toward the center, forming the planet's core. Lighter elements rose toward the surface, creating distinct layers. This process, called differentiation, established Earth's internal structure: a dense metallic core, a thick rocky mantle, and a thin rocky crust floating atop the mantle. The stratification happened relatively quickly in geological terms, perhaps within the first 100 million years of Earth's existence. We know this from studying the decay of hafnium isotopes into tungsten, which tells us when the core separated from the mantle. The oldest known rocks on Earth, found in the Nouveau-Jitup Greenstone Belt in Quebec, Canada, have been dated to approximately 4.28 billion years old. But we have evidence of even older materials. Tiny crystals of the mineral zircon, found in sedimentary rocks in Western Australia, have been dated to 4.4 billion years old. These resilient little crystals survived the tumultuous early Earth, weathering, erosion, and geological upheaval to give us a glimpse into our planet's distant past. They're the oldest solid materials found on Earth, time capsules from an alien world that existed where we stand today. The early atmosphere was nothing like the one we breathe now. Scientists believe it likely consisted of hydrogen and helium captured from the solar nebula. But these light gases escaped Earth's gravity and drifted into space. A second atmosphere formed through outgassing from volcanoes. Massive eruptions released water vapor, carbon dioxide, nitrogen, and smaller amounts of other gases. There was virtually no oxygen. This reducing atmosphere would have been toxic to most modern life forms. Based on atmospheric models, the sky might have appeared orange or brown from volcanic ash and chemical haze. Lightning storms would likely have been constant and dramatic, sparked by volcanic activity and the interaction of atmospheric gases. Water is essential to Earth as we know it, and its origin has been debated for decades. Some scientists thought Earth's oceans came primarily from icy comets and asteroids that bombarded the planet after it cooled. However, recent research from 2020 suggests that sufficient water to fill the oceans may have been present on Earth since the beginning of the planet's formation, locked in minerals and released as the planet evolved. Measurements of hydrogen isotopes in ancient rocks support this idea. The water we drink today, the water in our cells, might have been part of Earth from its very beginning, cycling through rock, vapor, ice, and liquid for over 4 billion years. When water vapor in the atmosphere cooled enough to condense, it began to rain, and it rained. Though we can't know the exact duration, geological evidence suggests torrential downpours may have continued for thousands, perhaps millions of years as the surface gradually cooled. Water collected in low-lying areas, forming the first oceans. These primordial seas were hot, acidic, and rich in dissolved minerals. They were nothing like today's oceans, but they were crucial. In these warm, chemical-rich waters, protected from harsh, ultraviolet radiation, the first simple life forms would eventually emerge. The oceans became Earth's cradle of life, a protective womb where chemistry could slowly, patiently become biology. The shields that protect us. Earth has a powerful magnetic field that extends thousands of kilometers into space, creating a protective bubble called the magnetosphere. This invisible shield is generated deep within the planet's interior by the motion of molten iron and nickel in the outer core. As this electrically conductive liquid metal flows in convection currents, driven by heat escaping from the solid inner core, it creates electric currents. These electric currents, in turn, generate magnetic fields through a process called the geodynamo. It's a self-sustaining system, powered by Earth's internal heat and rotation, that has been protecting our planet for billions of years. The magnetosphere extends approximately 63,000 kilometers toward the Sun on Earth's day side, though this distance varies depending on solar wind conditions. On the night side, away from the Sun, it stretches out into a long magnetotail that reaches beyond 200 Earth radii into space. The shape isn't symmetrical because the solar wind, a constant stream of charged particles flowing outward from the Sun, compresses the magnetosphere on the sunward side while stretching it out behind Earth like a windsock. The boundary between Earth's magnetosphere and interplanetary space is called the magnetopause. Here, the pressure of Earth's magnetic field balances the pressure of the solar wind. Without the magnetosphere, life on Earth's surface would face serious challenges, perhaps impossibilities. The solar wind consists of high-energy protons, electrons, and other charged particles traveling at speeds between 200 and 1,000 kilometers per second. These particles carry enough energy to strip away atmospheric gases molecule by molecule, a process called atmospheric erosion. We've seen this happen on Mars, which lost most of its atmosphere after its magnetic field shut down billions of years ago. Studies of carbon dioxide loss from Mars's atmosphere suggest that the dissipation of the magnetic field played a major role in atmospheric erosion. Based on what we understand about Mars' history, its atmosphere was once thick enough to support liquid water on its surface, but without magnetic protection, the solar wind gradually stripped it away over billions of years, leaving the cold, dry, nearly airless planet we see today. Earth's magnetic field deflects most of these charged particles, channeling them around the planet and preventing them from reaching the surface. Some particles do penetrate the magnetic shield, particularly near the poles where the field lines converge. When these high-energy particles collide with atoms and molecules in Earth's upper atmosphere, they excite those atoms, causing them to emit light. This creates the aurora borealis in the northern hemisphere and the aurora australis in the southern hemisphere. These shimmering curtains of green, red, blue, and purple light are a visible reminder of the invisible protection surrounding our planet. The strength of Earth's magnetic field at the surface ranges from 25 to 65 microteslas, depending on location. To give you a sense of scale, a refrigerator magnet produces a field of about 5,000 microteslas, roughly 100 times stronger. But Earth's magnetic field affects a vastly larger volume of space, and its strength doesn't depend on how strong it is in absolute terms, but rather on its ability to deflect charged particles across thousands of kilometers. Evidence from ancient rocks suggests Earth's magnetic field established itself approximately 3.5 billion years ago, relatively early in the planet's history. We know this from studying ancient rocks that contain magnetic minerals. When these minerals crystallize from molten rock, they align themselves with the prevailing magnetic field, like tiny compass needles frozen in stone. By analyzing the orientation of magnetic minerals in rocks of different ages, scientists can reconstruct the history of Earth's magnetic field. This field is not static. The magnetic north and south poles wander gradually over time, drifting hundreds of kilometers over centuries. Currently, magnetic north is moving away from Canada towards Siberia at a rate of about 55 kilometers per year. Even more dramatically, Earth's magnetic field completely reverses polarity every few 100,000 years on average, though the timing is irregular. During a reversal, north becomes south, and south becomes north. The last reversal happened approximately 770,000 years ago. We're not sure exactly what causes these reversals, but they likely result from complex dynamics in the molten outer core. The reversal process isn't instantaneous. It can take several thousand years to complete. During the transition, the magnetic field weakens significantly and becomes more complex, sometimes developing multiple poles. Despite what some dramatic depictions suggest, the fossil record shows no clear evidence that these reversals cause mass extinctions or catastrophic climate changes. Life on Earth has survived hundreds of these magnetic flips without major disruptions. Alongside the magnetic field, Earth developed another crucial protection: the ozone layer. Ozone is a molecule consisting of 3 oxygen atoms, written as O3. It forms when ordinary oxygen molecules, O2, are split apart by high-energy ultraviolet radiation from the sun. The freed oxygen atoms then combine with other oxygen molecules to create ozone. This happens primarily in the stratosphere, a layer of the atmosphere between 15 and 35 kilometers above Earth's surface. About 90% of Earth's ozone resides in this stratospheric layer. The ozone layer absorbs most of the sun's harmful ultraviolet radiation before it reaches Earth's surface. Ultraviolet light comes in three types: UVA, UVB, and UVC. The ozone layer blocks virtually all UVC and most UVB radiation. This protection is essential for life. UVB radiation damages DNA, causes skin cancer and cataracts in animals, and inhibits photosynthesis in plants and phytoplankton. Without the ozone layer, complex life on land would be impossible. Simple organisms might survive in the oceans, protected by water, but Earth's surface would remain a hostile environment. The ozone layer formed gradually as oxygen accumulated in Earth's atmosphere. This brings us to one of the most important events in Earth's history, the Great Oxidation Event. About 2.4 billion years ago, cyanobacteria, simple photosynthetic microorganisms, began releasing oxygen as a waste product of photosynthesis. For hundreds of millions of years, this oxygen reacted with iron and other minerals dissolved in the oceans and exposed on land surfaces, binding with them and preventing oxygen from accumulating in the atmosphere. You can see evidence of this in banded iron formations, distinctive layers of iron-rich rock deposited during this period. Eventually, after most readily available iron and other oxygen-hungry minerals had been oxidized, oxygen began to build up in the atmosphere. This was actually toxic to many organisms that had evolved in the oxygen-free environment. The oxygen revolution caused a mass extinction of anaerobic life forms, but it also opened up new possibilities. Oxygen-breathing organisms can extract far more energy from food than anaerobic organisms can. Much later, around 500 million years ago, when oxygen levels had risen sufficiently, the ozone layer formed in the upper atmosphere, protecting the surface from ultraviolet radiation. Together, these changes set the stage for complex multicellular life to evolve and eventually colonize the land. The ozone layer continues to protect us today, but it faced a serious threat in the late 20th century. Human-produced chemicals called chlorofluorocarbons, or CFCs, were widely used in refrigerators, air conditioners, aerosol sprays, and industrial processes. When these chemicals drifted up into the stratosphere, ultraviolet radiation broke them apart, releasing chlorine atoms. Each chlorine atom can destroy thousands of ozone molecules through a catalytic chain reaction. Scientists discovered massive ozone depletion over Antarctica in the 1980s, a phenomenon dubbed the ozone hole. The international community responded with remarkable speed and cooperation. The Montreal Protocol, signed in 1987, phased out the production of CFCs and related compounds. It's considered one of the most successful environmental treaties in history. Thanks to these efforts, the ozone layer has begun to recover. Scientists estimate it will return to pre-1980s levels by around 2060. It's a rare example of humanity identifying a global environmental problem and taking effective action to solve it. The restless surface. Earth's surface is divided into massive slabs of rock called tectonic plates. There are 7 or 8 major plates, depending on how you count them, and numerous smaller ones. These plates float on a partially molten layer of the mantle called the asthenosphere, which behaves like an extremely viscous fluid over geological timescales. The plates move relative to one another at rates varying from a few millimeters to over 10 centimeters per year. That's about as fast as your fingernails or hair grows. Slow by human standards, but over millions of years, these movements reshape entire continents and ocean basins. The theory explaining this movement is called plate tectonics, and it revolutionized Earth science in the 1960s. But the ideas behind it go back further. In 1912, a German meteorologist named Alfred Wegener proposed that the continents had once been joined in a supercontinent he called Pangaea, meaning all Earth in ancient Greek. He suggested this landmass broke apart and the continents drifted to their current positions. Wegener noticed that the coastlines of South America and Africa fit together like puzzle pieces. He found identical fossils of plants and animals on widely separated continents. Plants like the seed fern Glossopteris appeared in rocks on multiple continents that are now thousands of kilometers apart. Animals like Mesosaurus, a small freshwater reptile, left fossils in both Brazil and Western Africa. Since Mesosaurus could only swim in fresh water, it couldn't have crossed the Atlantic Ocean. Wegener argued these organisms had lived side by side when the continents were joined. He also discovered matching rock formations and mountain ranges on opposite sides of oceans. The Appalachian Mountains in North America and similar ranges in Scotland and Scandinavia share the same rock types, ages, and structural features suggesting they were once part of a single mountain chain. Wegener found evidence of ancient glaciation in tropical regions, with grooves carved by glaciers and deposits of glacial debris in places that are now far too warm for ice sheets. He proposed that these continents had been located near the South Pole when the glaciation occurred and had since drifted to warmer latitudes. Despite this compelling evidence, most scientists rejected Wegener's ideas. Why? Partly because he was a meteorologist rather than a geologist, and the scientific establishment didn't take him seriously, but mainly because he couldn't explain how solid continents could move through solid ocean floor. What mechanism could possibly push entire continents across the Earth's surface? Wegener proposed that Earth's rotation or tidal forces might drive continental movement, but physicists showed these forces were far too weak. Without a credible mechanism, continental drift remained a fringe idea for decades. Wegener died in 1930 during an expedition in Greenland, never seeing his theory vindicated. The breakthrough came from an unexpected source: the ocean floor. During World War II and the Cold War, navies developed sensitive instruments to map the seafloor and detect submarines. These instruments revealed astonishing features. The ocean floor wasn't flat and featureless. It contained enormous underwater mountain ranges called mid-ocean ridges, stretching for thousands of kilometers across every ocean basin. And it contained deep trenches, some plunging more than 10 kilometers below sea level. The ocean floor showed patterns nobody had anticipated. It was younger than expected, nowhere older than about 200 million years, while continental rocks dated back billions of years. Scientists measuring the magnetic properties of oceanic rocks discovered something remarkable. The rocks displayed alternating magnetic stripes running parallel to mid-ocean ridges. These stripes recorded reversals in Earth's magnetic field. As molten rock emerged from the ridge and solidified, magnetic minerals within it aligned with Earth's magnetic field at that moment. As the seafloor spread away from the ridge, new rock formed, recording the current magnetic orientation. When the field reversed, the new rock recorded the opposite polarity. The result was a striped pattern of magnetic anomalies, like a tape recording of Earth's magnetic history, symmetrical on both sides of the ridge. This seafloor spreading provided the mechanism Wegener had lacked. New oceanic crust forms at mid-ocean ridges, where tectonic plates pull apart and molten rock rises from below to fill the gap. The new crust pushes older crust away from the ridge in both directions. Meanwhile, at deep ocean trenches, old oceanic crust plunges back into the mantle in a process called subduction. This recycling of crust keeps the Earth in balance. New crust forms at ridges, old crust destroys itself in trenches, and the continents, embedded in the plates, ride along like passengers on slowly moving rafts. By the mid-1960s, the pieces fell into place. Scientists like Harry Hess, who proposed seafloor spreading in 1960, Robert Dietz, and others integrated these discoveries with continental drift and formulated plate tectonic theory. The Earth's lithosphere, its rigid outer shell consisting of the crust and uppermost mantle, is broken into plates. These plates move because of convection currents in the underlying mantle, driven by heat from Earth's core and radioactive decay. Where plates move apart at divergent boundaries, new crust forms. Where plates collide at convergent boundaries, one plate may slide beneath another, creating mountains, earthquakes, and volcanoes. Where plates slide past each other at transform boundaries, they generate earthquakes, but little volcanic activity. This theory explains so much that it puzzled geologists. It explained the distribution of earthquakes, which cluster along plate boundaries rather than occurring randomly. It explained the ring of volcanoes around the Pacific Ocean, the so-called Ring of Fire, where oceanic plates subduct beneath continental plates. It explained mountain building, as when the Indian plate collided with the Eurasian plate about 50 million years ago, crumpling the crust upward to form the Himalayas, Earth's highest mountain range. The collision continues today, pushing the Himalayas higher at a rate of about 5 millimeters per year. It explained why ocean crust is young, nowhere more than 200 million years old, while continental crust includes rocks over 4 billion years old. Ocean crust recycles through subduction, but continental crust is too buoyant to subduct easily, so it persists and accumulates over geological time. The continents have been wandering across Earth's surface for billions of years, periodically coming together and breaking apart in great cycles. About 300 million years ago, during the late Paleozoic era, the continents assembled into Pangaea, the supercontinent Wegener proposed. Before Pangaea, there was Pannotia, which formed around 600 million years ago. Before that, Rodinia assembled roughly 1 billion years ago. The oldest known supercontinent, which formed about 1.8 billion years ago, is sometimes called Columbia or Nuna. These supercontinents don't last forever. Internal heat causes the mantle beneath them to warm up, creating upwelling currents that tear the supercontinent apart. The cycle of assembly and breakup, driven by mantle convection, takes several 100 million years. Pangaea began breaking apart about 200 million years ago, during the early Mesozoic era. The Atlantic Ocean opened as the Americas separated from Europe and Africa, a process that continues today. India broke free from the southern supercontinent Gondwana and drifted north toward Asia, eventually colliding to form the Himalayas. Australia separated from Antarctica and moved northward. These movements continue today at measurable rates. The Atlantic Ocean widens by a few centimeters each year as new crust forms at the mid-Atlantic ridge. The Pacific Ocean shrinks by a similar amount as its edges are consumed in subduction zones. Africa is slowly splitting apart along the East African Rift, a zone of volcanic and seismic activity stretching thousands of kilometers. Eventually, perhaps in a few million years, part of East Africa will separate from the rest of the continent, creating a new ocean. The Mediterranean Sea will close as Africa continues moving north toward Europe. And far in the future, perhaps 250 million years from now, the continents will assemble into a new supercontinent, which scientists have dubbed Pangaea Proxima or Pangaea Ultima, though the exact configuration remains speculative. Plate tectonics shapes our world in countless ways, beyond just moving continents. It creates the geography that influences climate patterns and ocean currents. Mountain ranges like the Himalayas, Andes, and Alps, all formed by plate collisions, create rain shadows by forcing air to rise and cool as it crosses them. Moist air approaching mountains from one side rises, cools, expands, and drops its moisture as precipitation on the windward slopes. By the time the air descends on the other side, it's dry, creating arid conditions in the rain shadow. The Atacama Desert in Chile exists because the Andes block moisture from the Amazon basin. The deserts of Central Asia exist partly because the Himalayas and Tibetan Plateau block moisture from the Indian Ocean. It generates earthquakes and tsunamis that, while sometimes devastating, are inevitable consequences of a dynamic planet. Most earthquakes occur along plate boundaries where tectonic stress accumulates and is suddenly released. Transform boundaries, where plates slide past each other, generate earthquakes, but usually not tsunamis, because the motion is mostly horizontal. The San Andreas Fault in California is a transform boundary where the Pacific Plate slides northwest past the North American Plate at about 5 centimeters per year. Divergent boundaries, where plates pull apart, generate smaller earthquakes as new crust fractures and settles. Convergent boundaries, especially subduction zones, generate the largest and most dangerous earthquakes. When stress at the interface between converging plates exceeds the strength of the rocks, sudden slippage occurs. releasing energy as seismic waves and potentially lifting or dropping large sections of seafloor, displacing enormous volumes of water and generating tsunamis. Plate tectonics cycles carbon between the atmosphere and Earth's interior, helping regulate Earth's climate over geological timescales. As we discussed earlier, carbon dioxide dissolved in rainweather's rocks, and rivers carry the dissolved carbon to the ocean, where it's incorporated into shells and sediments. These carbon-rich sediments subduct at trenches, carrying carbon into the mantle. Some of this carbon returns to the atmosphere through volcanic eruptions. This carbon cycle operates over millions of years, much slower than the annual cycle of photosynthesis and respiration, but crucial for long-term climate regulation. Without plate tectonics constantly recycling carbon, all of Earth's carbon dioxide would eventually be locked up in rocks, leaving the atmosphere without enough greenhouse warming to prevent the oceans from freezing. Some scientists argue that plate tectonics may be essential for complex life to evolve and persist on a planet. It maintains diverse habitats as continents drift to different latitudes and climates, creating evolutionary pressures that drive adaptation and diversification. It regulates atmospheric composition through the carbon cycle, preventing runaway greenhouse or icehouse conditions. It creates geological activity, volcanism, and mountain building that may have helped concentrate minerals and create the chemical conditions necessary for life's origin and early evolution. It generates a magnetic field through the geodynamo in the liquid outer core, protecting the atmosphere from solar wind erosion. Without plate tectonics, Earth might be a geologically dead world like Mars, with a frozen or evaporated ocean and little atmosphere. However, we don't know for certain whether plate tectonics is necessary for life. Earth is the only planet we know with both plate tectonics and life, so we can't compare to other examples. Some scientists argue that a planet without plate tectonics could still support life if it had other ways to regulate climate and maintain habitable conditions. A thick atmosphere might provide enough greenhouse warming even without active carbon cycling. Volcanic activity driven by heat from radioactive decay rather than plate tectonics might release gases to maintain an atmosphere. Life might adapt to more extreme conditions than we see on Earth. These are open questions that future discoveries, perhaps from studying exoplanets or finding life elsewhere in our solar system, might help answer. Into the abyss. If you could drain all the water from Earth's oceans, you'd reveal a landscape more dramatic than anything on dry land. Vast abyssal plains stretch flat and smooth for thousands of kilometers, covered in fine sediment. Underwater mountain ranges tower higher than the Himalayas, with peaks and valleys sculpted by geological forces. And cutting through the sea floor are deep, narrow gashes called ocean trenches, some of which plunge to depths that would swallow Mount Everest with room to spare. Ocean trenches form where tectonic plates converge, and one plate subducts beneath another. As the denser oceanic plate bends downward into the mantle, it creates a deep, V-shaped depression in the seafloor. These trenches are typically 50 to 100 kilometers wide and 3 to 4 kilometers deeper than the surrounding ocean floor. though they can extend for thousands of kilometers in length. There are about 50,000 kilometers of ocean trenches worldwide, mostly ringing the Pacific Ocean as part of what's sometimes called the Ring of Fire. The Pacific Plate and other oceanic plates are subducting beneath continental plates around the ocean's margins, creating both deep trenches and chains of volcanoes. The deepest part of any ocean on Earth is the Challenger Deep, located in the Mariana Trench in the western Pacific Ocean. It reaches a depth of nearly 11,000 meters below sea level, with the most recent measurements placing it at 10,994 meters or 36,070 feet. That's almost 7 miles straight down. To put this in perspective, Mount Everest, the highest mountain on Earth at 8,848 meters above sea level, could fit inside the Mariana Trench with over 2 kilometers to spare. The pressure at this depth is crushing, over 1,000 times atmospheric pressure at sea level, equivalent to about 12,400 tons per square meter. If you tried to descend in an ordinary submarine, it would be crushed like a tin can. The environment in the deepest trenches is extreme in every way. It's cold, hovering just above freezing at around 2 to 4 degrees Celsius, despite being relatively close to the equator. The intense pressure from the weight of kilometers of water above creates conditions unlike anywhere else on Earth's surface. And it's dark, completely and utterly dark, because sunlight can't penetrate more than about 1,000 meters into the ocean. Below this depth, called the photic zone, the ocean is a world of perpetual night. No photosynthesis can occur, no plants grow, yet life persists. The Challenger Deep was first measured in 1951 by the British Royal Navy ship HMS Challenger 2, which gave the location its name, carrying forward the legacy of the original HMS Challenger's pioneering oceanographic expedition in the 1870s. The first people to reach this incredible depth were Swiss oceanographer Jacques Piccard and US Navy Lieutenant Don Walsh, who descended in the bathyscaphe Trieste on January 23, 1960. The Trieste was a remarkable craft, essentially a large steel sphere designed to withstand extreme pressure, attached to large tanks filled with gasoline for buoyancy. The descent took nearly 5 hours as they slowly dropped through the darkness. They spent 20 minutes on the bottom, where they observed small flatfish and shrimp through their viewport, proving that life exists even in Earth's deepest places. The ascent took over 3 hours. Since that first descent, only a handful of people have visited Challenger Deep. Film director James Cameron made a solo dive in 2012 in a specially designed submersible called Deep Sea Challenger, spending several hours on the sea floor and collecting samples. More recently, Victor Vescovo has made multiple dives as part of the 5 Deeps expedition, reaching the deepest points in all 5 oceans. Each expedition has discovered new species and learned more about this alien environment. In 2019, Vescovo's dive found plastic waste and candy wrappers at the bottom of the Mariana Trench, a sobering reminder that human impact reaches even the most remote places on Earth. Despite the extreme conditions, trenches support unique ecosystems adapted to life in the Hadal zone. This term comes from Hades, the Greek underworld, and refers to ocean depths below 6,000 meters. Organisms living there have evolved remarkable adaptations. Many lack gas-filled organs like swim bladders that would collapse under pressure. Instead, their bodies are made mostly of water and gelatinous material that's incompressible. They are often small, slow-moving, and energy efficient because food is scarce at these depths. Many have translucent or white bodies since there's no light and no need for pigmentation. Some produce their own light through bioluminescence, creating an eerie glow in the darkness through chemical reactions in specialized organs. These hadal zones are fed by organic material drifting down from the sunlit surface layers, a constant rain of dead plankton, fecal matter, and other detritus called marine snow. This material can take weeks to drift down through the water column. Scavengers on the seafloor feed on this material, processing the nutrients that sink from above. Predators feed on the scavengers, forming food chains that depend entirely on whatever falls from the productive surface waters thousands of meters above. Near hydrothermal vents and cold seeps in trenches, chemosynthetic bacteria convert chemical energy from hydrogen sulfide, methane, or other compounds into organic matter, forming the base of food webs independent of sunlight. These bacteria support communities of giant tube worms, clams, mussels, crabs, and fish in the deep darkness. Studying ocean trenches has revealed much about Earth's geology and the processes shaping our planet. They are places where oceanic crust returns to the mantle, completing the rock cycle that has been operating for billions of years. Sediments deposited on the ocean floor over millions of years subduct into the trench, carrying water and carbon into Earth's interior. This affects mantle chemistry and volcanic activity in profound ways. When water-rich sediments heat up as they descend, they release fluids that lower the melting point of surrounding rock, generating magma that rises to create volcanic arcs parallel to the trench. The Japanese islands formed this way, as did the Aleutian Islands in Alaska and the Andes Mountains in South America. Trenches are also sites of intense seismic activity. As plates grind past each other in the subduction zone, stress builds in the rocks until it's released suddenly in earthquakes. The interface between the subducting and overriding plates, called the megathrust fault, can produce some of the most powerful earthquakes on Earth. Some of the most devastating earthquakes in recorded history have occurred at subduction zones. The 2011 Tohoku earthquake off Japan, which triggered a massive tsunami and the Fukushima nuclear disaster, was a magnitude 9.1 megathrust earthquake at a subduction zone. The earthquake ruptured a fault segment about 500 kilometers long and 200 kilometers wide. The tsunami waves reached heights of over 40 meters in some locations. The 2004 Indian Ocean earthquake and tsunami, which killed over 230,000 people in 14 countries, resulted from a magnitude 9.1 to 9.3 earthquake at the Sunda Trench, where the Indian plate subducts beneath the Burma plate. These terrible events remind us that Earth is dynamic and that human timescales don't always align with geological processes. But trenches aren't just sites of destruction. They play crucial roles in regulating Earth's climate over millions of years by removing carbon dioxide from the atmosphere and locking it in subducted sediments. When carbonate minerals and organic carbon sink to the seafloor and then get dragged into the mantle through subduction, they remove carbon from the surface environment for millions of years. Some of this carbon eventually returns through volcanic emissions, but the balance between subduction and volcanism helps regulate atmospheric carbon dioxide over geological timescales. Trenches contribute to the rock cycle, creating new minerals and rocks through the intense heat and pressure of metamorphism in subduction zones, and they're natural laboratories for understanding extremophile life, organisms that thrive in conditions we once thought impossible for life to exist. Conditions of extreme pressure, darkness, and cold. These discoveries expand our understanding of where life might exist, both in Earth's deep biosphere and potentially on other worlds like Jupiter's moon, Europa, or Saturn's moon, Enceladus, which have subsurface oceans beneath ice shells. The march of time and life. Earth's history spans 4.54 billion years, a time span so vast that our minds struggle to comprehend it. To make sense of this immensity, geologists have developed the geologic time scale, dividing Earth's history into eons, eras, periods, epochs, and ages, based on major changes in rock layers and fossil records. It's a framework for understanding when things happened and how they relate to one another. The largest divisions are eons. Earth's history includes 4 eons. The Hadean eon, from Earth's formation until about 4 billion years ago, was the hellish early period we discussed earlier. The Archean eon, from 4 billion to 2.5 billion years ago, saw the first solid crust form, the first oceans develop, and the emergence of the earliest life. The Proterozoic eon, from 2.5 billion to 538 million years ago, featured massive changes, including the oxygenation of the atmosphere and the evolution of complex cells. The Phanerozoic eon, from 538 million years ago to the present, is characterized by abundant fossils and the diversification of complex life. Life emerged surprisingly early in Earth's history. The oldest undisputed evidence of life dates back at least 3.5 billion years, possibly earlier. Simple single-celled organisms, likely similar to modern bacteria, appeared in the oceans. We don't know exactly how life began. Different hypotheses suggest it may have started in warm tidal pools, in deep-sea hydrothermal vents, or in some other environment where organic chemicals could concentrate and react. The earliest life was almost certainly anaerobic, living without oxygen in a world where oxygen was scarce or absent. For billions of years, life remained simple and microscopic, but these simple organisms profoundly changed the planet. Cyanobacteria evolved the ability to perform photosynthesis, using sunlight to convert carbon dioxide and water into organic compounds and oxygen. For hundreds of millions of years, the oxygen they produced reacted with iron and other minerals. But eventually, oxygen began accumulating in the atmosphere, leading to the Great Oxidation Event around 2.4 billion years ago. This transformed Earth's chemistry and climate, caused mass extinction of anaerobic organisms, and enabled the evolution of complex life. Another crucial development was the evolution of eukaryotic cells, cells with nuclei and other internal structures. These appeared around 2 billion years ago. Eukaryotes are fundamentally different from bacteria and archaea. They're larger, more complex, and capable of greater diversity. Around 1.2 billion years ago, eukaryotes evolved sexual reproduction, mixing genetic material from two parents. This greatly accelerated evolution by creating more genetic diversity. Multicellular life appeared around 600 million years ago, though simple colonial organisms may have existed earlier. The first large, complex organisms were soft-bodied creatures known from the Ediacaran period. Then, about 540 million years ago, Earth experienced the Cambrian explosion, a relatively brief period when most major animal groups appeared in the fossil record. Within about 20 to 25 million years, creatures with shells, exoskeletons, and hard body parts diversified dramatically. Scientists continue to debate the exact causes of this explosion, though rising oxygen levels, the evolution of predator-prey relationships, and genetic innovations all likely played important roles. Life colonized the land much later than it colonized the oceans. Simple plants and fungi may have established themselves on land around 500 million years ago. Animals followed, with arthropods like insects and arachnids among the first. Vertebrates, animals with backbones, moved onto land around 370 million years ago, during the Devonian period. These early tetrapods evolved from lobe-finned fish and gave rise to amphibians, reptiles, mammals, and eventually humans. Earth has experienced 5 major mass extinction events during the Phanerozoic Eon, periods when a large proportion of species died out in geologically short times. The most severe was the Permian-Triassic extinction about 252 million years ago, which killed over 90% of marine species and 70% of land vertebrates. While the exact cause remains debated, evidence points to massive volcanic eruptions in Siberia, dramatic climate change, and ocean acidification as likely contributing factors. The most famous extinction event is the Cretaceous Paleogene extinction 66 million years ago, which killed the non-avian dinosaurs. An asteroid, roughly 10 kilometers in diameter, struck Earth near what is now the Yucatan Peninsula in Mexico. The impact released energy equivalent to billions of nuclear bombs, creating a crater over 180 kilometers wide. It triggered earthquakes, tsunamis, and global wildfires. Dust and sulfur aerosols thrown into the atmosphere blocked sunlight, causing an impact winter that devastated photosynthesis-based food chains. The dinosaurs' extinction opened ecological niches that allowed mammals to diversify and eventually dominate land ecosystems. Humans are newcomers to Earth's story. Our species, Homo sapiens, evolved in Africa around 300,000 years ago, give or take. That's 0.0066% of Earth's total history. If Earth's history were compressed into a single year, modern humans would appear on December 31st at about 11:58 p.m. All of recorded human history would flash by in the final seconds before midnight. We've been here for an eye blink compared to trilobites, which thrived for about 270 million years, or sharks, which have existed for over 400 million years. The layered Earth. If you could slice Earth in half and look inside, you'd see that it's organized in layers, like a very complex onion. These layers differ in composition, temperature, and physical properties. We can't directly observe most of Earth's interior. The deepest humans have drilled is the Kola Super Deep borehole in Russia, which reached just over 12 kilometers depth, less than 0.2% of the way to Earth's center. Yet we know a tremendous amount about Earth's interior thanks to seismology, the study of earthquake waves. When an earthquake occurs, it generates different types of seismic waves that travel through Earth. Primary waves, or P waves, are compression waves that can travel through solids, liquids, and gases. Secondary waves, or S waves, are shear waves that can only travel through solids. By analyzing how these waves travel through Earth, how fast they move, how they bend and reflect the boundaries between different materials, scientists have mapped Earth's internal structure in remarkable detail. The outermost layer is the crust, the thin, solid shell on which we live. Continental crust averages about 30 to 50 kilometers thick, though it's thicker beneath mountain ranges like the Himalayas. Oceanic crust is thinner, typically about 7 kilometers. The crust is composed primarily of relatively light rocks like granite on continents and basalt in ocean basins. Despite being the only layer we directly experience, it makes up less than 1% of Earth's total volume. Beneath the crust lies the mantle, a thick layer of hot, dense rock extending to a depth of about 2,900 kilometers. The mantle makes up about 84% of Earth's volume. It's mostly solid, but it's hot enough to flow very slowly over geological time, behaving like an extremely viscous fluid. This flow drives plate tectonics through convection currents. Hot material rises from deeper in the mantle, spreads horizontally beneath the crust, cools, and sinks back down, creating a slow churning motion. The mantle isn't uniform. The upper mantle includes the asthenosphere, a partially molten zone where rock is close to its melting point and can flow relatively easily. Above this is the lithosphere, which includes the crust and uppermost mantle. The lithosphere is rigid and broken into tectonic plates. Deeper in the mantle, pressure increases dramatically. Around 660 kilometers down, minerals undergo phase transitions, rearranging their crystal structures to pack more efficiently under pressure. These transitions create boundaries that seismic waves reveal. The lower mantle extends from about 660 to 2,900 kilometers depth. Here, pressures reach over 1 million times atmospheric pressure, and temperatures exceed 2,000 degrees Celsius. The rock is solid, but it's under such extreme conditions that it behaves differently than surface rocks. Near the bottom of the mantle, there's a mysterious layer called the D double prime layer. a few hundred kilometers thick. It may contain remnants of subducted ocean crust or be chemically distinct for other reasons. Scientists are still investigating its properties and origin. Below the mantle lies Earth's core, divided into two parts. The outer core extends from about 2,900 to 5,100 kilometers depth. It's composed primarily of liquid iron and nickel, with some lighter elements like sulfur, oxygen, or silicon mixed in. Based on seismic studies and high-pressure experiments, scientists estimate temperatures range from about 4,000 to 6,000 degrees Celsius. This liquid metal layer is where Earth's magnetic field originates through the geodynamo process. The inner core, from 5,100 kilometers to Earth's center at 6,371 kilometers depth, is solid, despite being even hotter than the outer core. Models suggest temperatures may reach 5,400 degrees Celsius or more, though measuring conditions at Earth's center remains challenging. The immense pressure, over 3.5 million times atmospheric pressure, forces the iron into a solid crystalline state. The inner core is roughly the size of the Moon. Studies of seismic waves suggest it may rotate slightly faster than the rest of the planet, though this remains an active area of research. As the core slowly cools over billions of years, the inner core gradually grows as liquid iron from the outer core freezes onto it. Earth's core contains about 1/3 of the planet's mass, despite making up only about 15% of its volume. The core is incredibly dense, about 12 to 13 times denser than water. This density comes from iron and nickel being heavy elements. When Earth was molten early in its history, these dense metals sank to the center through differentiation. Heat flows from Earth's interior to its surface, left over from the planet's formation and continuously generated by radioactive decay of uranium, thorium, and potassium in the crust and mantle. This heat drives mantle convection, plate tectonics, and volcanic activity. It powers the geodynamo that creates our magnetic field. Without this internal heat, Earth would be a geologically dead world like the Moon, with no plate tectonics, no volcanism, no magnetic field, and likely no life as we know it. The fact that Earth's interior remains hot and active after 4.5 billion years is crucial to our existence. The water planet. From space, Earth's most striking feature is its blue color. That blue comes from water, specifically the oceans that cover about 71% of Earth's surface. If you divided Earth's surface into equal areas, only 29% would be land. The rest would be ocean. This abundance of liquid water is one of Earth's most distinctive characteristics and essential for life as we know it. The total volume of water on Earth is estimated at about 1.4 billion cubic kilometers. That sounds like an enormous amount, and it is, but it represents only about 0.02% of Earth's total mass. If you gathered all Earth's water into a sphere, it would have a diameter of only about 1,380 kilometers, much smaller than the Moon. Most of this water, roughly 96.5%, resides in the oceans. The rest exists as ice in glaciers and ice sheets, groundwater, lakes, rivers, atmospheric water vapor, and in living organisms. Ocean water is salty, containing about 35 grams of dissolved salts per kilogram of seawater. That's about 3.5% salt by weight. The salt isn't just sodium chloride, though that's the most abundant component, making up about 85% of the dissolved salts. Ocean water also contains magnesium, calcium, potassium, sulfate, and many other dissolved minerals and trace elements. Every natural element can be found dissolved in seawater, at least in trace amounts. Rivers constantly wash minerals from land into the ocean through erosion and weathering of rocks. Rain dissolves minerals from soil and rock as it percolates through the ground. Streams and rivers carry these dissolved substances to the sea, adding about 4 billion tons of dissolved salts to the ocean each year. Hydrothermal vents on the sea floor release minerals directly from Earth's crust into the water, adding elements like iron, manganese, and sulfur. Water evaporates from the ocean surface, leaving salts behind, which concentrates them over time. Yet despite these inputs, ocean salinity remains remarkably stable. Interestingly, the ocean has maintained roughly the same salinity, around 3.5%, for hundreds of millions of years because various processes remove salt at about the same rate it's added, creating a dynamic equilibrium. Some salt gets trapped in evaporite deposits when shallow seas or isolated basins dry up, leaving thick layers of halite, rock salt, and gypsum that can be hundreds of meters thick. The Mediterranean Sea has dried up and refilled multiple times in its geological history, leaving massive salt deposits beneath the sea floor. Some salt gets incorporated into minerals forming on the seafloor through chemical reactions, particularly in hydrothermal systems where hot water reacts with rock. Some get subducted at ocean trenches, carried down into the mantle, along with oceanic crust and sediments. Marine organisms also remove dissolved minerals from seawater to build shells and skeletons. And when they die and sink to the sea floor, they lock these minerals away in sediments. This balance between input and removal keeps ocean salinity stable over geological timescales, even though individual basins like the Mediterranean Sea or Red Sea can have significantly different salinities due to local conditions like high evaporation rates or restricted water exchange with the open ocean. Freshwater makes up only about 2.5% of Earth's total water. Of that small fraction, nearly 70% is locked in ice caps and glaciers, primarily in Antarctica and Greenland. Antarctica alone holds about 90% of the world's ice and approximately 70% of its fresh water in an ice sheet that covers almost 14 million square kilometers and averages over 2 kilometers thick. If all of Antarctica's ice melted, which would require sustained warming over thousands of years and represents a worst-case scenario, global sea levels would rise by about 58 meters, enough to submerge most coastal cities and reshape coastlines worldwide. Greenland's ice sheet, covering about 80% of Greenland's surface and averaging about 1.7 kilometers thick, would contribute another 7 meters to sea level if it melted completely. These ice sheets are not static. They flow slowly from their centers toward their edges, where ice carves off into the ocean as icebergs. Scientists monitor these ice sheets carefully because they respond to climate change, and sea level rise from melting ice sheets represents one of the most significant long-term impacts of global warming. Only about 0.3% of Earth's freshwater is found in lakes, rivers, and swamps. This is the water most accessible to humans and land ecosystems, and it represents just 0.0075% of all water on Earth. When we consider that much of this water is polluted or unavailable, it becomes clear that accessible fresh water is a precious resource. Water moves continuously through Earth's hydrological cycle, the circulation of water between the ocean, atmosphere, land, and living organisms. The sun heats ocean and land surfaces, evaporating water into the atmosphere. Plants also release water vapor through transpiration. Water vapor rises, cools, and condenses into clouds. When conditions are right, water falls as precipitation, rain, snow, sleet, or hail. Some precipitation soaks into the ground, recharging groundwater. Some flows across the surface in streams and rivers, eventually returning to the ocean. The cycle continues endlessly, powered by solar energy. This water cycle has profound effects on Earth's climate and habitability. Water has an extremely high heat capacity, meaning it can absorb or release large amounts of heat with relatively small temperature changes. Oceans store enormous amounts of heat, moderating global temperatures and transporting heat from the tropics towards the poles through ocean currents. Water's phase changes between solid, liquid, and gas absorb or release heat, affecting weather patterns and climate. Evaporation cools surfaces. Condensation and precipitation release heat into the atmosphere. These processes help redistribute energy around the planet. Earth has experienced multiple ice ages throughout its history, periods when global temperatures dropped, ice sheets expanded, and sea levels fell as water became locked in glaciers. The most recent ice age, called the Quaternary glaciation, began about 2.6 million years ago and includes cycles of glacial and interglacial periods. During glacial maxima, ice sheets covered large parts of North America, Europe, and Asia. Sea levels dropped by over 100 meters, exposing continental shelves and creating land bridges. The Bering Land Bridge between Asia and North America allowed humans and animals to migrate between continents. We're currently in an interglacial period called the Holocene, which began about 11,700 years ago as the last glacial period ended. The massive ice sheets retreated, sea levels rose, and the climate warmed. This relatively stable warm period allowed human civilizations to develop agriculture, build cities, and flourish. However, Earth's climate is now changing rapidly due to human activities, primarily the burning of fossil fuels that releases carbon dioxide and other greenhouse gases. Global temperatures are rising faster than at any time in the past 2,000 years. Ice sheets and glaciers are melting. Sea levels are rise high. These changes, will profoundly affect future generations. Recent research has revealed hidden water reservoirs within Earth's interior. A mineral called ringwoodite, found in the transition zone between the upper and lower mantle, can contain significant amounts of water in its crystal structure. Scientists estimate this deep reservoir might hold as much water as all the oceans combined. Though it's not liquid water, it's chemically bound in minerals under extreme temperature and pressure. This discovery changes our understanding of Earth's water cycle, suggesting water circulates between the surface and deep interior through subduction and volcanic activity over millions of years. The envelope of air above Earth's surface extends the atmosphere, a thin envelope of gas held in place by gravity. From sea level to the edge of space, the atmosphere is only about 100 kilometers thick. That might sound substantial, but relative to Earth's size, it's incredibly thin. If Earth were the size of an apple, the atmosphere would be no thicker than the apple's skin. Yet this delicate layer is essential for life. It provides the air we breathe, shields us from harmful radiation, moderates temperatures, and creates weather patterns that distribute water around the planet. Earth's atmosphere is divided into layers based on temperature changes with altitude. The troposphere extends from the surface up to about 10 to 15 kilometers, varying with latitude and season. It's thickest at the equator, where warm air causes the tropopause to bulge upward, and thinnest at the poles where cold, dense air keeps it lower. This is where we live and where virtually all weather occurs. Temperature decreases with altitude in the troposphere at a rate of about 6.5 degrees Celsius per kilometer, a pattern called the environmental lapse rate. This happens because the sun's energy heats the ground, and the ground heats the air above it. So the farther you go from the heat source, the colder it gets. At the troposphere's top is the tropopause, a boundary layer where temperature stops decreasing and begins to increase. Above the tropopause lies the stratosphere, extending to about 50 kilometers altitude. Temperature increases with altitude in the stratosphere, opposite of the trend in the troposphere, because ozone absorbs ultraviolet radiation from the sun, converting it to heat and warming this layer. Commercial aircraft fly in the lower stratosphere between about 10 and 12 kilometers altitude to avoid weather and turbulence and to take advantage of the stable air and thinner atmosphere that reduces drag. The ozone layer resides in the stratosphere, concentrated between 15 and 35 kilometers altitude, with peak concentrations around 20 to 25 kilometers. This protective shield absorbs most of the sun's harmful ultraviolet radiation, preventing it from reaching Earth's surface where it would damage DNA and harm living organisms. The mesosphere extends from about 50 to 85 kilometers altitude. Temperature decreases with altitude again in this layer, dropping to the coldest temperatures found anywhere in Earth's atmosphere. Near the top of the mesosphere, temperatures can reach minus 100 degrees Celsius or even colder. Despite being high in the atmosphere and closer to the sun than the surface, it's cold here because the air is so thin it can't hold much heat and there's no ozone to absorb radiation and warm it. Meteors usually burn up in the mesosphere due to friction with air molecules. The spectacular shooting stars we see on clear nights are typically the result of small particles, often no larger than grains of sand, heating up to thousands of degrees and vaporizing as they slam into the atmosphere at speeds of tens of kilometers per second. Most never reach the ground, their atoms scattering into the upper atmosphere. Above the mesosphere lies the thermosphere, extending from about 85 kilometers to between 500 and 1,000 kilometers altitude. Temperature increases dramatically with altitude in the thermosphere, potentially reaching up to 1,500 degrees Celsius or more during periods of high solar activity, though temperature becomes somewhat meaningless at these altitudes because the air is so thin. There are so few molecules that they rarely collide with each other, and they carry very little total heat energy, despite their high individual velocities. An object in the thermosphere wouldn't feel hot because there aren't enough molecules hitting it to transfer significant heat. The International Space Station orbits in the thermosphere between 330 and 430 kilometers altitude, where it experiences enough atmospheric drag that it must periodically boost its orbit to avoid gradually falling back to Earth. Aurora occur in the thermosphere when charged particles from the solar wind, channeled by Earth's magnetic field, collide with atmospheric atoms and molecules, exciting them and causing them to emit light in shimmering curtains of green, red, blue, and purple. The exosphere is the outermost layer, gradually fading into the vacuum of space. It extends from the top of the thermosphere to about 10,000 kilometers altitude, though the boundary between the exosphere and interplanetary space is not sharply defined. It's more of a gradual transition. Atoms and molecules here are so spread out that they rarely collide with each other. They can travel dozens or even hundreds of kilometers between collisions. Light gases like hydrogen and helium can escape Earth's gravity from the exosphere, slowly leaking into space. Earth loses about 90 tons of atmosphere to space every day through this process, mostly hydrogen and helium. That sounds like a lot, but it's negligible compared to Earth's total atmospheric mass of about 5 quadrillion tons. At this rate, it would take trillions of years to lose the atmosphere. The composition of Earth's atmosphere has changed dramatically over geological time, and it's quite different from the atmospheres of other planets in our solar system. Today's atmosphere is about 78% nitrogen gas and 21% oxygen gas, with small amounts of argon, carbon dioxide, water vapor, and trace gases making up the remaining 1%. The nitrogen and argon are largely chemically inert, not participating in most atmospheric chemistry or biological processes. They're essentially filler gases that provide atmospheric pressure. Oxygen and carbon dioxide, despite being minor constituents in terms of percentage, are chemically active and essential for life as we know it. Oxygen is reactive and quickly combines with other elements through oxidation, rusting iron, burning fuels, and supporting respiration in animals. Without constant replenishment by photosynthetic organisms, plants, algae, and cyanobacteria, atmospheric oxygen would gradually disappear as it reacts with surface rocks and dissolved chemicals in the ocean. As we discussed earlier, oxygen accumulated in the atmosphere thanks to photosynthetic organisms beginning about 2.4 billion years ago. This transformed Earth's atmosphere from a reducing environment where hydrogen-rich gases dominated to an oxidizing environment where oxygen could react with and alter surface chemistry. Carbon dioxide levels have varied significantly throughout Earth's history, influencing climate in profound ways. During the Carboniferous period, about 300 million years ago, carbon dioxide levels were relatively low, possibly around 300 parts per million or less, while oxygen levels reached about 35%. The high oxygen allowed giant insects and other arthropods to evolve, including dragonflies with wingspans of 70 centimeters and millipedes over 2 meters long. Arthropods breathe through small tubes called tracheae that rely on diffusion of oxygen, which works much better when atmospheric oxygen is high. More recently, during ice ages, carbon dioxide levels dropped to around 180 parts per million as cold oceans absorbed more of the gas. During warm interglacial periods, levels rose to about 280 parts per million. Before the Industrial Revolution, which began in the mid-1700s, carbon dioxide had been stable at about 280 parts per million for thousands of years, based on measurements from ice cores. Human activities, primarily burning fossil fuels like coal, oil, and natural gas, have increased atmospheric carbon dioxide to over 420 parts per million as of 2024, a level not seen in at least 3 million years. This increase has happened remarkably fast in geological terms over just 250 years, and is causing Earth's climate to warm. Carbon dioxide is a greenhouse gas, meaning it traps heat in the atmosphere. Sunlight passes through the atmosphere and warms Earth's surface. The warm surface radiates heat as infrared radiation. Greenhouse gases absorb some of this infrared radiation and re-emit it in all directions, including back toward the surface, keeping the lower atmosphere warmer than it would be otherwise. Earth's atmosphere creates weather through the interaction of solar heating, atmospheric pressure, humidity, and Earth's rotation. The sun heats the equator more intensely than the poles because the sun's rays strike the equator more directly, concentrating their energy over a smaller area, while they strike the poles at an angle, spreading the same energy over a larger area. This temperature difference drives air circulation. Warm air rises at the equator, creating a zone of low pressure. This rising air cools as it expands and moves towards the poles at high altitude. As it cools, it becomes denser and sinks at mid-latitudes around 30 degrees north and south, creating zones of high pressure. From these high-pressure zones, some air flows back toward the equator near the surface, completing a circulation cell called a Hadley cell. Other air flows toward the poles, creating mid-latitude circulation patterns. Earth's rotation deflects these air movements through the Coriolis effect, named after French mathematician Gustave Gaspard Coriolis, who described it in 1835. As Earth rotates, Points at the equator move faster than points at higher latitudes because they have farther to travel in the same amount of time. When air moves from one latitude to another, it carries its rotational velocity with it. Air moving from the equator toward the poles is deflected to the east, to the right in the northern hemisphere, and to the left in the southern hemisphere. Air moving from the poles toward the equator is deflected to the west. This creates prevailing wind patterns. The trade winds blow from east to west in the tropics. The westerlies blow from west to east in mid-latitudes. The polar easterlies blow from east to west near the poles. These wind patterns have shaped human history, powering sailing ships that carried explorers, traders, and colonizers across oceans. Jet streams are narrow bands of fast-flowing air in the upper troposphere and lower stratosphere, typically between about 7 and 12 kilometers altitude. They flow from west to east in both hemispheres at speeds that can exceed 300 kilometers per hour, though they meander north and south in wavy patterns. The polar jet stream, found at mid-latitudes around 60 degrees, forms at the boundary between cold polar air and warmer mid-latitude air. The subtropical jet stream forms around 30 degrees latitude. These fast-moving rivers of air influence weather by steering storms and air masses. When the jet stream flows in a relatively straight path from west to east, weather patterns remain fairly stable and predictable. When it develops large meanders, bending far to the north and south in amplified waves, it can create unusual weather by bringing Arctic air far south or tropical air far north, and by causing weather systems to stall in one location for extended periods, leading to prolonged heat waves, cold snaps, or precipitation events. The atmosphere also protects us from meteorites and space debris. Every day, an estimated 100 tons of material from space enters Earth's atmosphere. Most of it is small, cosmic dust and tiny particles shed by comets. As these objects plunge into the atmosphere at speeds ranging from about 11 kilometers per second, the minimum speed needed to reach Earth from space up to 70 kilometers per second for objects entering head-on against Earth's motion around the Sun. Friction with air molecules heats them to thousands of degrees. The heat comes not primarily from friction in the traditional sense, but from ram pressure as the object compresses air in front of it faster than the air can get out of the way, creating a shock wave that generates intense heat. Most objects burn up completely before reaching the ground, disintegrating at altitudes between 60 and 100 kilometers. We see this as meteors or shooting stars. Only larger objects, greater than about 100 meters in diameter, with enough mass to survive the passage through the atmosphere, strike Earth's surface as meteorites. Smaller objects either burn up or are slowed down enough that they drift gently to the ground as micrometeorites. The atmosphere acts like a shield, disintegrating cosmic debris that would otherwise bombard the surface. The mesosphere extends from about 50 to 85 kilometers. Temperature decreases with altitude again in this layer. It's the coldest part of Earth's atmosphere, reaching temperatures as low as minus 100 degrees Celsius near the top. Meteors usually burn up in the mesosphere due to friction with air molecules. The spectacular shooting stars we see on clear nights are typically the result of small particles, often no larger than grains of sand, heating up and vaporizing in this layer. Above the mesosphere lies the thermosphere, extending from about 85 kilometers to between 500 and 1,000 kilometers altitude. Temperature increases dramatically with altitude in the thermosphere, reaching up to 1,500 degrees Celsius or more, though temperature becomes somewhat meaningless at these altitudes because the air is so thin. The International Space Station orbits in the thermosphere between 330 and 430 kilometers altitude. Aurora occur in the thermosphere when charged particles from the solar wind collide with atmospheric atoms and molecules. The exosphere is the outermost layer, gradually fading into the vacuum of space. Atoms and molecules here are so spread out that they rarely collide with each other. This layer extends up to about 10,000 kilometers, though the boundary between the exosphere and interplanetary space is not sharply defined. Light gases like hydrogen and helium can escape Earth's gravity from the exosphere, slowly leaking into space. The composition of Earth's atmosphere has changed dramatically over geological time. Today's atmosphere is about 78% nitrogen and 21% oxygen, with small amounts of argon, carbon dioxide, water vapor, and trace gases. The nitrogen and argon are largely chemically inert, not participating in most atmospheric chemistry. Oxygen and carbon dioxide, despite being minor constituents, are chemically active and essential for life. As we discussed earlier, oxygen accumulated in the atmosphere thanks to photosynthetic organisms. Carbon dioxide levels have varied throughout Earth's history, influencing climate. During the Carboniferous period, about 300 million years ago, carbon dioxide levels were low and oxygen levels reached about 35%, allowing giant insects and other arthropods to evolve. More recently, during ice ages, carbon dioxide levels dropped to around 180 parts per million. During warm interglacial periods, they rose to about 280 parts per million. Before the Industrial Revolution, carbon dioxide had been stable at about 280 parts per million for thousands of years. Human activities have increased it to over 420 parts per million, a level not seen in millions of years. Earth's atmosphere creates weather through the interaction of solar heating, atmospheric pressure, humidity, and Earth's rotation. The sun heats the equator more than the poles, creating temperature differences that drive air circulation. Warm air rises at the equator, flows toward the poles at high altitude, cools, sinks at mid-latitudes, and returns toward the equator near the surface. Earth's rotation deflects these air movements through the Coriolis effect, creating prevailing wind patterns like the trade winds, westerlies, and polar easterlies. Jet streams are narrow bands of fast-flowing air in the upper troposphere and lower stratosphere. They flow from west to east in both hemispheres at speeds that can exceed 300 kilometers per hour. Jet streams influence weather by steering storms and air masses. A strong, stable jet stream keeps weather patterns predictable. A weak, meandering jet stream can create unusual weather, like prolonged heat waves or cold snaps. The atmosphere also protects us from meteorites. Every day, tons of material from space enters Earth's atmosphere. Most of it, fortunately, is small. As these objects plunge into the atmosphere at speeds of tens of kilometers per second, friction with air molecules heats them to thousands of degrees. Most burn up completely before reaching the ground. Only larger objects, greater than about 100 meters in diameter, survive passage through the atmosphere to strike Earth's surface as meteorites. The atmosphere acts like a shield, disintegrating cosmic debris that would otherwise bombard the surface. Our singular home, Earth, orbits the Sun at an average distance of about 150 million kilometers, a distance astronomers call 1 astronomical unit, which serves as a standard measurement for distances within our solar system. At this distance, Earth receives just the right amount of solar energy to maintain temperatures suitable for liquid water and life. The amount of solar radiation Earth receives, called the solar constant, is about 1,361 watts per square meter at the top of the atmosphere, though only about half of that reaches the surface after absorption and reflection by the atmosphere and clouds. If Earth were significantly closer to the Sun, it would receive more energy and would be too hot. Water would evaporate more readily, and water vapor is itself a greenhouse gas, creating a positive feedback loop. More evaporation leads to more water vapor, which traps more heat, which causes more evaporation. This runaway greenhouse effect happened on Venus, our neighboring planet toward the Sun. Venus is nearly the same size as Earth and sits just inside the inner edge of the Sun's habitable zone, but its thick carbon dioxide atmosphere creates surface temperatures exceeding 450 degrees Celsius, hot enough to melt lead. Any oceans Venus may have had in its early history evaporated long ago, and the water vapor was broken apart by ultraviolet radiation, with the hydrogen escaping to space and the oxygen reacting with surface rocks. If Earth was significantly farther from the Sun, it would receive less energy and would be too cold. Water would freeze permanently, locking it away in ice and preventing the liquid water essential for life as we know it. This appears to be what happened on Mars, our outward neighbor. Mars orbits near the outer edge of the habitable zone. Evidence suggests Mars once had liquid water on its surface, with ancient river valleys, lake beds, and possible ocean basins visible in satellite imagery. But Mars is smaller than Earth, with only about half Earth's diameter and roughly 1/10 Earth's mass. Its lower gravity couldn't hold on to its atmosphere as effectively, especially after its magnetic field shut down, leaving the atmosphere vulnerable to erosion by the solar wind. Today, Mars is cold and dry, with average surface temperatures around -60 degrees Celsius and atmospheric pressure less than 1% of Earth's. Any liquid water on the surface quickly freezes or evaporates into the thin atmosphere. This region around a star, where conditions allow liquid water to exist on a planet's surface, is called the habitable zone, or more colloquially, the Goldilocks zone, after the fairy tale character who preferred things neither too hot nor too cold. Earth sits comfortably within the Sun's habitable zone, but distance from the Sun is only part of the equation for habitability. Venus and Mars demonstrate that being in or near the habitable zone doesn't guarantee a habitable planet. Many other factors matter. Size matters significantly. Earth's mass is large enough to retain a substantial atmosphere through gravitational attraction and to maintain geological activity driven by internal heat. Smaller planets cool faster because they have higher surface area relative to their volume, allowing heat to escape more readily. As a planet's interior cools, its core solidifies, shutting down the magnetic field generated by convection of molten metal. Without a magnetic field, the atmosphere becomes vulnerable to erosion by the solar wind. Plate tectonics also slows or stops as the interior cools and the mantle becomes too rigid to convect effectively. Mars, with about half Earth's diameter and 1/10 Earth's mass, lost most of its atmosphere after its magnetic field disappeared billions of years ago. Its core cooled and solidified, ending both the magnetic dynamo and vigorous geological activity. Mercury, even smaller, at about 40% Earth's diameter, never had much atmosphere to begin with, due to its proximity to the Sun and low gravity, and it shows no signs of current geological activity. Earth's atmosphere contains just enough greenhouse gases to keep the planet comfortably warm without overheating. Carbon dioxide, water vapor, methane, and other greenhouse gases trap some of the Sun's heat, maintaining an average global temperature around 15 degrees Celsius. Without any greenhouse effect, with an atmosphere that was completely transparent to infrared radiation, Earth's average temperature would be about minus 18 degrees Celsius, well below the freezing point of water. The oceans would freeze over, making liquid water scarce and life as we know it difficult or impossible. With too strong a greenhouse effect, temperatures would soar uncontrollably, as happened on Venus. Earth's carbon cycle, involving weathering of rocks, ocean chemistry, plate tectonics, volcanic emissions, and biological activity, has regulated atmospheric carbon dioxide levels for billions of years through negative feedback mechanisms, keeping climate within a range suitable for life. Here's how this long-term carbon cycle works. Carbon dioxide in the atmosphere dissolves in rainwater, forming weak carbonic acid. This acidic rain slowly weathers rocks on land, dissolving minerals and releasing calcium and other ions. Rivers carry these dissolved ions to the ocean. Marine organisms like corals, mollusks, and plankton use the calcium and carbon dioxide dissolved in seawater to build shells and skeletons made of calcium carbonate. When these organisms die, their shells sink to the sea floor, accumulating over millions of years into thick layers of carbonate sediments like limestone. Plate tectonics carries these carbonate sediments to subduction zones, where they're dragged down into the mantle. Heat and pressure release the carbon dioxide from the rocks, and it returns to the atmosphere through volcanic eruptions, completing the cycle. This creates a natural thermostat. If Earth gets too warm, weathering accelerates because chemical reactions proceed faster at higher temperatures and because there's more rainfall. More weathering removes more carbon dioxide from the atmosphere, which reduces the greenhouse effect and cools the planet. If Earth gets too cold, weathering slows because chemical reactions proceed slower at lower temperatures and because there's less rainfall, with more precipitation falling as snow. With less weathering, carbon dioxide accumulates in the atmosphere from volcanic emissions, strengthening the greenhouse effect and warming the planet. This negative feedback system has helped keep Earth's climate relatively stable for billions of years, though it operates on timescales of hundreds of thousands to millions of years, too slow to counteract rapid human-caused climate change happening over decades and centuries. Earth's moon plays a crucial role in maintaining conditions favorable for life. The moon's gravity stabilizes Earth's axial tilt at about 23.5 degrees. Without the moon, computer simulations suggest Earth's axial tilt would vary chaotically over millions of years, swinging from nearly 0 degrees, where the equator faces the sun and the poles are in perpetual cold, to perhaps 85 degrees or more, where the poles alternate between pointing nearly at the sun and away from it. This axial tilt creates our seasons as different hemispheres receive varying amounts of sunlight throughout the year. Stable seasons allow ecosystems to adapt and organisms to develop life cycles synchronized with predictable environmental changes. Wild swings in axial tilt would create extreme and unpredictable climate variations, making it difficult for complex life to evolve and persist. The moon also creates tides in Earth's oceans. The gravitational pull of the moon, and to a lesser extent the sun, creates two bulges of water on opposite sides of Earth. The bulge nearest the moon is pulled toward it. The bulge on the far side occurs because the moon pulls the solid Earth away from the water more than it pulls the water itself, since the solid Earth is closer to the moon on that side. As Earth rotates, these bulges appear to move around the planet, creating high and low tides. Tides mix ocean waters vertically and horizontally, distributing nutrients and oxygen and preventing stagnation. They create tidal zones, regions alternately covered and exposed by tides, which are harsh environments where organisms must withstand periods of submersion in water and exposure to air, sun, and desiccation. Natural selection in these zones may have helped early life develop adaptations needed to colonize land, making the tidal zone a possible stepping stone from fully aquatic to fully terrestrial life. Earth's biodiversity is staggering. Though we've only begun to catalogue it, scientists have identified and formally named about 1.7 million species of plants, animals, fungi, and microorganisms. But this is likely just a fraction of Earth's total biodiversity. Conservative estimates for the total number of species range from 5 million to perhaps 15 million, though some researchers studying microbial diversity suggest the number could be much higher. A single gram of soil can contain thousands of species of bacteria, most of which have never been formally described. The vast majority of unknown species are likely microorganisms, insects, and other small creatures that are difficult to find, identify, and study. Life exists in almost every environment on Earth, demonstrating remarkable adaptability. Organisms thrive in hot springs and deep-sea hydrothermal vents, where temperatures exceed 100 degrees Celsius. Thermophilic bacteria and archaea live in Yellowstone's Grand Prismatic Spring at temperatures around 70 degrees Celsius, creating the vibrant colors with their pigments. Hyperthermophilic archaea near deep-sea vents can survive temperatures above 120 degrees Celsius under the high pressure that prevents water from boiling. Microbes live in permanently frozen Antarctic soil, where temperatures rarely rise above freezing. Bacteria have been found in clouds, high in the atmosphere, possibly playing roles in cloud formation and precipitation. Life exists deep underground in fractures in rock kilometers below the surface, where chemolith autotrophic bacteria extract energy from chemical reactions involving rock and water, completely independent of sunlight. The deepest parts of the ocean, with crushing pressure and perpetual darkness, support unique ecosystems of fish, invertebrates, and microbes. Some organisms survive extreme radiation, desiccation, or other harsh conditions that would kill most life forms. Tardigrades, also called water bears, are microscopic animals less than a millimeter long that can survive conditions fatal to almost all other animals. They can withstand temperatures from near absolute zero to over 150 degrees Celsius. They can survive pressures 6 times greater than the deepest ocean trenches. They can endure radiation doses hundreds of times higher than would kill a human. They can go without water for decades, entering a state called cryptobiosis, where they shut down their metabolism to almost nothing and wait for favorable conditions to return. Some bacteria form endospores, dormant structures that can survive for millions of years in suspended animation until conditions improve. Life's ability to adapt and persist in extreme environments expands our understanding of where life might exist elsewhere in the universe. If life can thrive in Earth's most hostile places, perhaps it can exist in the subsurface oceans of Europa or Enceladus, in the methane lakes of Titan, in the soil of Mars, or in environments we haven't yet imagined. The discovery of extremophiles on Earth has fundamentally changed astrobiology, the study of life in the universe. We now know that habitable encompasses a much wider range of conditions than we once thought. Earth is the only place in the universe where we know life exists. Despite decades of searching, we've found no convincing evidence of life on any other world yet. We've sent probes to Mars, studied meteorites from Mars and the Moon, examined samples returned from the Moon and from asteroids, listened for radio signals from intelligent civilizations, and observed thousands of exoplanets around other stars. So far, we've found no definitive signs of life beyond Earth. This makes Earth profoundly special and our responsibility to protect it immense. The delicate balance of conditions that allows life to flourish here, liquid water, protective atmosphere, and magnetic field, plate tectonics maintaining a stable climate, might be rare in the cosmos. Earth might be one of a very small number of life-bearing worlds in the galaxy or even the universe. Or perhaps life is common, and we simply haven't found other examples yet, because we haven't looked hard enough, in enough places, with sensitive enough instruments, or because life is hard to detect at interstellar distances. The universe is vast, containing roughly 2 trillion galaxies, each with hundreds of billions of stars. Many of those stars have planets. The sheer numbers suggest that even if the probability of life emerging on any given planet is very small, there should be many worlds with life somewhere out there. But until we find evidence, we can't be sure. The Fermi paradox, named after physicist Enrico Fermi, asks, if the universe is teeming with life and intelligent civilizations are common, where is everybody? Why haven't we detected them or seen evidence of their technology? Various answers have been proposed, from we're alone to they exist but are too far away to detect, to they're here but we don't recognize them, but we don't yet know which, if any, is correct. Either way, whether we're alone or one among many, Earth is our home, the only home humanity has ever known, and the only home we can reach with current technology. The nearest star system, Alpha Centauri, is over 4 light-years away. With current spacecraft, it would take tens of thousands of years to reach it. Interstellar travel remains in the realm of science fiction for now. Earth is where we are, where we evolved, where all of human history has unfolded. Every person who has ever lived was born here. Every city, every artwork, every scientific discovery, every war and peace, everything that defines our species happened on this small blue planet. As astronomer Carl Sagan eloquently said when looking at the famous pale blue dot image of Earth taken by Voyager 1 from the edge of the solar system, this distant dot is home. It's us, and it's the only home we have. The final thoughts. As we drift toward the end of our journey through 100 facts about Earth, it's worth reflecting on what all these facts tell us. Earth is ancient beyond imagination. It's dynamic, constantly changing through plate tectonics, erosion, volcanism, and life itself. It's protective, with magnetic fields and atmospheric shields preserving the fragile biosphere. It's resilient, having survived asteroid impacts, volcanic mega-eruptions, ice ages, and mass extinctions. Yet life persists and adapts, and it's beautiful, a blue and white marble spinning in the darkness of space, the only place we know where consciousness has arisen to contemplate itself and its origins. Every atom in your body was forged in the cores of dying stars billions of years ago. The iron in your blood, the calcium in your bones, the oxygen you breathe, all came from stellar nucleosynthesis and supernova explosions. These atoms drifted through space for eons before coming together in the solar nebula, forming Earth, and eventually becoming part of you. You are literally made of stardust, a fact that never loses its wonder. The water you drink is the same water that dinosaurs drank, that early humans carried in clay pots, that fell as rain on ancient Pangaea. Water cycles endlessly through ocean, atmosphere, and land, connecting all life across deep time. The oxygen you breathe was produced by countless generations of plants and cyanobacteria through photosynthesis. You're breathing in the waste products of ancient life forms transformed into the very essence you need to survive. Earth's story is still being written. The planet will continue to evolve. Long after humans are gone, continents will drift to new configurations. Mountain ranges will rise and erode away. Species will evolve, flourish, and go extinct. The sun will gradually grow brighter and hotter as it ages. Models of stellar evolution suggest this will eventually make Earth uninhabitable for complex life, perhaps in about 1 billion years. Long before that, in just a few 100 million years, Earth's oceans may begin to evaporate as solar radiation intensifies. But for now, in this present moment, Earth is a paradise for life, a rare oasis in the cosmic desert. We're living in a remarkable time to be aware of Earth's story. Previous generations didn't know about plate tectonics or the age of the Earth. They couldn't see images of our planet from space. They didn't understand evolution or the vast spans of geological time. We're privileged to live in an era when science has revealed these wonders, when we can trace our lineage back through millions of years of evolution, when we can see our planet as a whole and understand our place in the cosmos. This knowledge brings responsibility. We now understand that Earth's climate can change, that species can go extinct, that resources are finite. We've altered the planet significantly through agriculture, industry, and urbanization. The climate is warming faster than at any time in human history. Species are going extinct at rates not seen since the dinosaurs died out. Ocean chemistry is changing. Forests are shrinking. These changes will affect future generations, and we have a moral obligation to address them. But there's also hope. Humans are adaptable and inventive. We've developed technologies that can help mitigate climate change and protect ecosystems. We're learning to use renewable energy, reduce waste, and preserve wilderness. The Montreal Protocol showed that when humanity recognizes a global environmental problem, we can work together to solve it. The ozone layer is recovering because nations cooperated to phase out harmful chemicals. Understanding Earth's history gives perspective. The planet has endured far worse than anything humans can throw at it. Evidence suggests Earth survived what's called the Late Heavy Bombardment, a period when asteroids pummeled the surface, though the exact timing and severity remain debated. It survived the Snowball Earth episodes, periods when geological evidence indicates much or all of the planet may have been covered in ice. It survived massive volcanic eruptions that would have darkened the skies for years. It survived asteroid impacts that killed most species. Earth will persist long after we're gone. The question isn't whether Earth will survive, but whether we'll create conditions that allow human civilization to flourish, and whether we'll preserve the incredible biodiversity that shares this planet with us. You are part of Earth's story. The atoms in your body have cycled through countless organisms over billions of years. You're connected to every living thing through the shared chemistry of life, and the distant common ancestors we all share. When you breathe, you're participating in the ancient exchange of gases that sustained life for billions of years. When you drink water, you're part of the hydrological cycle that's operated since the oceans formed. You're not separate from nature. You are nature, a conscious part of Earth, observing and contemplating itself. As you rest tonight, as sleep slowly approaches, remember that you're lying on the surface of a planet hurtling through space at 30 kilometers per second. You're protected by an invisible magnetic shield deflecting deadly radiation. You're breathing an atmosphere created by billions of years of life. You're warmed by heat from a star 93 million miles away, and by heat escaping from Earth's core, forged in the planet's violent birth. You're part of a story 4.5 billion years in the making, a story of transformation, of creation, of destruction, of resilience, of beauty, and of wonder. Earth is our home, our only home, floating in the vastness of space. It's a small world, fragile and finite, yet teeming with life and possibility. It's ancient beyond comprehension, yet young compared to the universe. It's been here long before us and will persist long after we're gone. We're temporary inhabitants of this beautiful blue world, passengers on a journey through time and space that began long ago and will continue long after our brief moment is over. Sleep well, knowing you're cradled by a planet that has nurtured life for billions of years. Rest easy, protected by shields of magnetism and air that have guarded Earth since long before your ancestors walked upright. Dream peacefully, part of a living biosphere that stretches from the deepest ocean trenches to the highest mountains, from frozen poles to tropical rainforests. You are home. You are part of Earth. And Earth, in all its ancient majesty and endless wonder, is part of you. If you're still awake, thank you for joining me on this journey through Earth's story. I hope you found these facts interesting and that they helped you relax. If this video brought you peace or sparked your curiosity, please consider liking and subscribing to Whispered Knowledge. Your support helps others discover these quiet explorations. Until next time, rest well, sleep deeply, and remember that you're part of something vast and ancient and beautiful. Good night.